All right, folks, let's get started. So first of all, welcome to the Sedona Community Office Hour today, and we're very excited to have you here. And so as usual, so let's first give you a quick overview about what Sedona is uh, and what we are doing for Sedona, right? So first of all, Sedona is an open source cluster computing engine for processing large scale geospatial data. And we have our website, sedona.apache.org, and we also have our GitHub, uh, also under Apache Sedona repo, and we also have a Twitter account. And if you're interested, please do follow us on Twitter and get the latest news. We also have our Discord account. So if you're interested to talk to any community members through live chat, please also sign up on our Discord server. And we also recently added our LinkedIn account, Apache Sedona LinkedIn account. So if you're also interested, please also follow us on LinkedIn to get the latest news. So let's move on. So the current status of Sedona. So Sedona is a project we started in 2015, and it became mature in 2017 and joined Apache Software Foundation in 2020. And it has more than 10,000 corporate users, and it has 118 contributors on GitHub, and it has 1.8 thousand stars on GitHub, and it has over 1.5 million downloads last month. Overall downloads has exceeded 26 million in total, and it is ranked among top 0.3% most downloaded package on PyPy. So lots of people are using Sedona. And as you can see, so all these logos on your right hand side, so lots of companies are using Sedona in production. And a quick overview about Sedona's system architecture. So as you can see here, Sedona has multiple layers. So the first layer is the spatial query processing layer on top. So it provides spatial SQL, Python, Scala, Java, and R API. So you can use whatever developer tools you like and talk to Sedona through those following query languages. And in this layer, we also provide distributed query algorithm that can take your spatial queries and run the query workload across machines in the cluster. It also comes with a spatial query optimizer that automatically decides what is the best query algorithm to run given a spatial query. And the second layer we have is called distributed spatial dataset layer, which is this layer you see here. It has multiple functions such as spatial partitioning, spatial indexing, and spatial data compression, and the spatial data serialization and deserialization. And the final layer is called distributed engine layer. So in this layer, we currently support multiple engines. So Apache Spark for batch processing, and Apache Flink for stream processing, as well as Snowflake. So we have a separate Snowflake plugin called Sedona Snow. We are providing that on Snowflake Marketplace. So Sedona releases. So in Sedona community, we are following the 3-month release cadence. So today, so in the past few months, we have been working on 2 releases actually. So 152 and 160. And these 2 releases took a little bit longer time. And today we are going to release 152. So the community has finished the voting process for 152, and we are all set. And after 152, we're going to release another one called 160. So as you can see here, so this time we are making 2 releases at the same time. So 152 is a maintenance release that contains couple bug fixes that fix the issues we introduced in 151. And in particular, in 160, so 160 is going to be a major release that have multiple new features, which we're going to be introduced that later in a few slides. So 162 has a breaking change. In 162, we are introducing Java 11. So basically, we compare Sedona against Java 11. That means you will no longer be able to run Sedona on Java 8. So just keep this in mind. And that's why we also introduce one more maintenance release, 152, right? So we want to make sure we fix as many bugs as possible before we move to a Java 11 release. Now, let's take a look at the new features in 160. As I mentioned, the 160 is a major release, and it's going to be out no later than the weekend of this, like the end of this week. So all the features has been completed for 160. Now let's give a quick overview about what functions we are introducing in 160. So first of all, it is compiled by Java 11, not Java 8. So we started to implement GeoParquet spec 1.1 support in 160 release, but it is still not completed yet. So we are looking at that now. And in particular, we are introducing Shapely 2.0 support in our Python interface. So in Sedona, in older Sedona versions, we have been supporting Shapely 1.0, and Shapely 2.0 reintroduced lots of breaking changes. So in the past 1 year, so we were not able to support that. So we recently fixed those breaking changes in Shapely 2.0. So which means now in Sedona 160, you'll be able to run Shapely UDF on Shapely 2.0 and use the new API, new functions introduced in Shapely 2.0. And another important thing is because we start to support Shapely 2.0, we're also able to support newer versions of GeoPandas. So any versions that is newer than GeoPandas 0.12. And if you didn't know, if you didn't know, so Sedona data frame to pandas function will actually give you a GeoPandas data frame directly. And the Sedona.create data frame function can give you a Sedona data frame also directly. So that means, so say you are using GeoPandas to read data and save data. So it can directly help you to talk to GeoPandas data frame, right? You can literally use GeoPandas to read any spatial data format and directly convert it to a Sedona data frame, and it will run the workload in parallel at scale. Another important thing we're adding in Sedona 160 is strong geography support. So I will give a deeper look on that. So basically, we allow users to run geography calculation on our on the geometry column in parallel, and give also accurate results. Okay, now let's take a deeper look at a few vector functions we introduced in Sedona 160. So first of all, for the strong geography support, we're adding the following file function. So st-base SRID, st-cross data line, st-shift longitude, and st-dwithin with spheral distance, st-buffer with spheral distance. So what does that mean? So st-base ID basically can automatically decide what is the best CRS for the coordinate you give, right? So that can help you to determine, so when you do ST transform, right? So what SID you should use to get an accurate result. ST cross data line helps you that you can automatically decide if a geometry is cross international data line or not. Because, you know, when you handle geography data across international data line, you're going to make sure so the calculation is correct, right? And in many cases, so the calculation might not be accurate. So you might want to do some special treatment on those geometries by call this ST cross data line manually and filter them out. And ST shift longitude will actually flip your the geometry that cross international data line, and it will actually help you to mitigate the issues when perform queries on the geography object. And ST deviating spheroid that allows you to specify a spheroid distance, so which is in meter. With this ST deviating spheroid in place, you no longer need to call the ST transform beforehand to transform your data to a meter-based CIS. And ST buffer spheroid, similarly, so ST buffer in the past, so it takes a buffer distance, but this buffer has to be in the same CIS of the input coordinates. So ST buffer spheroid allows you to specify a meter-based buffer directly. So which means it can actually work. You don't have to run ST transform anymore, right? And another function is called ST snap. And the third one is called ST polygonize. So ST snap will snap the vertex and segments of a geometry to a geometry's vertex. So this is similar to the PostGIS ST snap function. As you can see here in this figure, so we have a geometry like this one, like polygon geometries in the blue color, right? And we have another line string in the green color. And ST snap will try to snap the shape of the polygon to the shape of this line string, as you can see here. And depending on the tolerance threshold you give to ST snap, so it will try to snap the polygon to the line string as much as possible. All right. Another function is called ST polygonize. So what it does is it creates a geometry collection containing the polygons formed by the line work of a set of geometries. So it is also very similar to the function that is in PostGIS. So as you can see here, so this function is commonly used for people to form a polygon from a row network, for example. So say this is a row network, right? You can actually take a subset of the row network and form a polygon from that. Like this one is a polygon that you can construct through a number of row segments. So this is ST polygonize. And we also have a few new raster functions in Sedona 160. So two important ones. One is called RS interpolate. Another one is called RS reproject match. So RS interpolate is a very useful function. So what it does is, so it estimates the cell values by averaging the values of sample data points in the vicinity of each processing cells. So why do we need that? So in the raster data, you already have, right? So it is oftentimes having some sort of missing values in the image. And in some cases, the missing values are actually sometimes they're more than the observed values, right? So basically, which means you only have a few observed values in your raster images, and most of them are missing values. So in that case, in order to perform some sort of like query processing on that, you might want to actually average out might want to get an estimate of the missing values based on the observations you already have. So the figure down there is a very good example. If you look at this is the original raster, right? So you can see it only has a few observation values, right? The vast majority of the pixels, they're empty. So we call this RS interpolate function on that. It will actually get estimate values for each cell based on the values of nearby cells, as you can see here. So this will be a very helpful function for you to get an estimate of the values. Another function, as mentioned, is called RS reproject match. So what it does is it reprojects a raster to match the georeference CRS and envelope, our reference raster. So this is function that is very similar to the reproject match function in Rasterio X-ray. So let's take a look at this example. So we have two rasters, right? Raster 1 and raster 2. So we can use raster 2 as a reference raster to do reproject match on raster 1. And also keep it in mind, so raster 1 and raster 2, they have different spatial envelope. So their envelopes that are not 100% aligned with each other. So when you use raster 2 as a reference raster and do reproject match on raster 1, as you can see here, so we actually realigned raster 1 to according to raster 2. So some part of the image is now cropped off, right? And also, as you can see here, because of the georeference information, so raster 1 is also slightly rotated according to the rotation direction of the raster 2. And similarly, we can use raster 1 as the reference raster and apply that to raster 2 and ask raster 2 to reproject and match to raster 1. So in this case, you will see that so raster 2 got cropped up and its direction is also slightly rotated to match direction in raster 1. So there are many cases that the image is captured by satellite. So they're captured, they're looking at similar regions, but at different timestamps. So the images themselves are slightly mismatched. So this reproject match is oftentimes used to help people to realign those images that are captured by the satellite at different timestamps, right? And with that, you'll be able to perform queries, analytics on those images. Another important feature we are introducing in 160 is called Rasterio and NumPy integration. So basically, with this new release, you are able to write raster UDF, and in the raster UDF, you can call Rasterio function and NumPy function to directly perform any operations you want. So basically, in the raster object in Sedona Python, so we provide two functions called as NumPy and as Rasterio. And you will be able, based on given these two functions, you will be able to call additional functions available in NumPy and Rasterio. Now let's take a look at an example. So this is a raster UDF in Sedona, and we use NumPy function in this UDF. As you can see here, so we call raster as NumPy function to get a NumPy array. And then we call the function called mean that directly takes the mean value across all bands in the raster. So this is just a very simple UDF that calculates the mean. And you can implement that this way through one line of code. And then you can actually register that as a UDF, and run that on your entire raster data frame. You can basically apply this UDF to, hundreds, thousands of images in parallel. And you can also do this through Rasterio. Do the exact same thing, although Rasterio is a little bit more complicated and less convenient for those kind of array operations as opposed to NumPy. but still it provides lots of functions that you might find useful. So this Rasterio function does the exact same thing. So what it does is you call this as Rasterio function to get a Rasterio object from Sedona raster. And then you can call Rasterio native functions to perform all these kind of operations. And once you are done, we can register UDF, like the Rasterio UDF here. You can register that, and you can then apply that to all rasters in the data frame. And another interesting thing we have been working on in the Sedona community. So the bring geo to Apache Iceberg. So as you guys already know, so nowadays a lot of people are using Sedona on top of a lakehouse environment, on top of Delta Lake, on top of Iceberg, right? So in the past, Iceberg does not have native geometry type support. And so in the past few months, the Iceberg community has been very active on working with us and trying to add geometry support natively in Apache Iceberg. So now we are working with the Iceberg community and the Sedona community to introduce the geometry support in Iceberg. So basically, we are working with the Iceberg committers from Apple, and we are going to make two changes. So one change is to change Iceberg code base to understand geometry type, and we are also making change in Sedona code base. So Sedona can directly write geometry type to Iceberg. And in addition to the geometry type, we are also introducing native filter pushdown in Iceberg parquet and arrow files through partition transform. So basically, when you save data in Iceberg, you no longer you can also not only get benefit from the geometry type, and the queries on the geometry type data can also be accelerated through filter pushdown. And if you guys are interested, you can follow the progress here, and so you can also participate in the discussion. Okay. I think I can bring up some additional slides if you guys are interested, because I saw a few new folks here. All right. So since we saw a few new folks here, so I brought up some slides we use in our last community office hour, just in case you guys want to know that. So just a few slides about the geography support we recently added in Apache Sedona. So first of all, the problem of geospatial data, the geography data, right? So in the past, Sedona has been really focusing on the geometry data support. However, the support of geometry data runs into problems when it comes to spheral distance calculation or geodesic distance, right? So this is very simple because the strip of the Earth is not in a planar space, and also it is not in a perfect spheral shape. So if you look at this particular example, right? So many of those visualization software, they cannot actually handle the geometry data that cross international data line. So probably let me zoom in this one a little bit. So as you can see here, so this WKT polygon is a very simple example. This polygon actually crossed international data line, right? And if you visualize that through ordinary visualization software, it actually does not able to visualize that. This polygon is actually a polygon somewhere here. It's a very small polygon somewhere here. But if you put it in a visualization software, it does not understand that. It instead gives you a polygon that crosses the entire planet, as you can see here. So this is a very common problem in many of this kind of spatial software. So if you use that before, you probably already know the problem. And in Sedona 160, right, we have multiple functions added in order to mitigate these issues. First of all, ST-based RID, right? It gives you the most suitable meter-based CIS given a WGS84 geometry. And the ST cross international dataline, it allows you to detect if an object cross international dataline. And the shift longitude. Shift longitude will shift coordinates between minus 180 and 0 degree to positive 180 and 360 degrees, and vice versa. So you can use this together with ST intersect to mitigate issues of the data that cross the international data line. And also strong geography support for ST-DVZ with spheral distance. As you can see here, now in this release, we'll be able to specify meter-based distance in ST-DVZ. And Sedona is able to optimize this query. As you can see here, so this query is actually a distance join query. It has two tables, two geometry columns. It actually joining these two tables together based on meter-based distance. And Sedona Query Optimizer in this release going to be able to capture this query and perform optimized distributed spatial join on that. And similarly on ST buffer spiral. Now in this release, you will be able to perform ST buffer with the meter-based buffer in this function. And this function can also be put together in an ST intersect function. And you can use that as a spatial join. And Sedona will be able to understand it and optimize the query. And this ST buffer is also well designed. It can actually handle data that cross international data line. It will able to give you the correct buffer shape of the geometry. And in Sedona release, earlier version of Sedona release, we already introduced ST distance sphere and ST distance sphere and spiral. So this function also take meter-based distance, and it allow user to use it together with the spatial join query. And Sedona will be able to optimize that and run distributed spatial join query. So as you can see here, so this is an example of the ST distance sphere-based spatial join, and you can specify meter-based distance and find out all the possible candidate pairs that has less than this distance. All right, I think that's all I want to present today. And now I think it is time to for the community to have a roundtable introduction and some Q&A, right? So let me see here. We have a couple of folks here, and anyone want to introduce? Travis, do you want to introduce yourself?
Hey, yeah, I don't really have too much to say. This is really, really interesting stuff. Yeah, I'm just a engineer working at Maxar, and just interested in geospatial. And yeah, I've worked with, I came out to San Francisco to the GeoPerk sprint, so I saw where robots there, was able to test out some of their systems, and kind of looking forward to testing out the new version that's coming out. But yeah, I don't really have too much to say.
Yeah, no problem, no problem. Welcome to the community. And if you have any problem trying out Sedona or whereabouts, just feel free to let us know.
Okay,
Welcome.
thank you.
Kay, do you want to introduce yourself? Uh, okay. Uh, Hannah, do you want to introduce yourself? Not sure if I pronounced it right. All right. Uh, Furkan, do you want to introduce?
Hi, I've been contributing towards Apache Sedona since July last year, and I've been working alongside with Whereabouts since then, and I'm glad to be part of the community. Thank you, Gio.
Thank you. And Christine,
Oh, hey everyone. This is Christy, and I'm a PMC of Apache Sedona. And in the past week, I have tested several of the release candidates of the next release of Sedona, which is 1.5.2. And well, I hope it will be the most amazing release of Sedona. It has fixed quite a lot of the bugs of the previous version. So I'd like all you guys to try it out once it got released.
thank you. Uh, all right. So I think, Bill, do you want to introduce yourself?
Sure. Hey, folks. My name's Will. Work on the developer relations team at Whereabouts. I've been following the progress on this release for a while. So exciting to see it almost there. Looking forward to using it in production and helping folks analyze spatial data with it. Specifically, looking forward to a lot of the new raster functionality. That's pretty exciting area. So thanks everyone for joining.
Thank you, Bill. Ben, you want to introduce yourself?
Yeah, sure. Hey, everybody. I'm Ben. I lead go-to-market for robots and excited to be part of this community. Just wanted to be here to meet all of y'all.
Thank you, Ben. All right, folks. I think that's all for today. If you don't have any questions for me, please feel free to leave. But if you have any questions, I will be here and happy to answer any of that.
Gia, I guess maybe I'll ask you a question, something that I've been wondering about. With the Rasterio and NumPy integrations, you talked about the ability to create UDFs in both of those and sort of run those in parallel at scale. I wonder, is there kind of like a guideline for when you would leverage Rasterio over NumPy? I know that like the functionality is a bit different, but I'm just curious, like, are there specific use cases that folks have in mind for one versus the other?
Yeah, that's a very good question. So both of them can solve same problem in terms of general array-based operations, right? But NumPy, as you know, it is ordinary Python library that handle array data. So if you have like no very specific operations for the raster operations or spatial operations, then you can feel free to use NumPy since it has more generic functions and possibly more helper functions that can help you to quickly calculate some statistics or do some quick visualization on the data you have, right? But if you have some very special raster-based operations, you're going to choose Rasterio. For example, because Rasterio is a very specific library that's for users to read and process raster data, right? So it can read the CRS metadata of the raster image, right? It can also perform some special operations, for example, resample functions, reprojection functions on the raster images. So this is something that NumPy will not offer. So that will be the case that you want to use Rasterio for those kinds of very special operations.
Gotcha. That makes sense.
All right, folks. Since no questions and no new people coming in, so I'm gonna wrap it up. And yeah, I think that's it for today. And thanks for joining us. And thank you, guys. Bye.